Hello everyone. In this video we are going to study about banyan switches, how they can be used in implementation of interconnection networks. Then we will study about crossbar interconnection network. Then we will study about shuffle exchange interconnection network. So let's start with banyan switches, and this is the general structure of a banyan switch, where you can see that there are two inputs and two outputs. A 2 by 2 banyan switch has two inputs numbered 0 and 1 and two outputs numbered 0 and 1. Now here is a salient feature of banyan switch, and it goes like: the banyan switch has a switching control built into the switch itself. That means the control for the switching has been implemented inside the switching device itself. Now question might arise, how the information which arrives into the switch are routed to two different outputs. That means you must have a way out following which you can route output either towards the output port marked with 0 or to the output port marked with 1, and it goes here. Every information unit that comes into the banyan switch has a header that contains a bit indicating its destination, either 0 or 1. So here is the solution to the problem. Whatever information which arrives into the banyan switch, there is a bit associated with that information which contains the destination in terms of either 0 or 1. If the switch reads the bit and it has a value 0, then it sends the packet to its upper output. So if the information which has arrived into the banyan switch contains 0 in its first bit of the packet, then it will be routed towards this output. Now if the first bit of the packet has 1, then this output is routed towards the second output port, that is 1. Now by connecting this simple banyan switches, different interconnection networks have been implemented. For example, shuffle exchange network, omega network, butterfly network, etc., etc. Now today we will look into crossbar network at first. This is the basic diagram of a crossbar network. This numbers encircled in green circles are basically your processors. Now if you look into this block diagram, you can find that you have 8 processors in your multiprocessor system, and the address of the processors are 0, 1, 2, 3, 4, 5, 6, 7. The salient feature of this crossbar interconnection network is that all the processors are connected with each other via some switching devices. These tiny yellow circles are your switching devices. So have a look into the statement. A crossbar has every node of the network connected to every other node. Now, because any node can send simultaneous message to every other node in the system without conflicts, this network topology is basically non-blocking. You can see that each and every node is connected to each and every node via different paths. So, it can easily be inferred that multiple nodes can simultaneously communicate among themselves. There are no chances of conflicts are there. This topology thus becomes non-blocking. So, for example, say processor 2 is communicating with processor 0. Now, processor 1 wants to make communication with processor 3. So, it can follow the direct path which connects processor 1 to processor 3. In this way, this crossbar switching network becomes non-blocking. However, as there are so many switches and so many connections, it becomes very expensive. It will require very high bandwidth, and not too much scalability will be available here. Why? You can see into the figure that there are 8 processors into your system, but to connect these 8 processors you need 8 square, that is 64 switches to connect each of them with one another. If you count the yellow circles, you will find that there are 64 such yellow circles which basically represent switches connecting two processors among themselves. Now, as a generalization, we can say that if there are n number of processors in your system, the number of switches which will be required to implement this crossbar interconnection network will be n square, and in this way it becomes an expensive type of network. So this was the basic idea behind the crossbar network. Next we move to shuffle exchange interconnection network. This is basically a single stage interconnection network. Now, what is a stage in an interconnection network? It is basically the number of layers of switches which are there in between the interconnected processors. You can see that there is only a single layer of switches here, so this is a single stage interconnection network. Now, how this shuffle exchange interconnection network go? To understand that, let me draw a sequence of processors. Say you have 8 number of processors in your system and whose addresses are 0, 1, 2, 3, 4, 5, 6 and 7. These are basically your processors. So in your multiprocessor architecture, for this example, you have 8 number of processors are there. Now, as a rule, these processors will be connected among themselves something like this. The processor whose address is 0, it will be connected to itself. Processor whose address is 1, it will be connected to the processor whose address is 2. The processor whose address is 2, it will be connected to the processor whose address is 4. Processor which has 3 as its address will be connected to processor with address 6. Processor with address 4 will be connected to processor with address 1. Processor with address 5 will be connected to processor with address 3. Processor which has address 6 will be connected to the, am I right here? Yes, processor whose address is 6 will be connected to processor which has address 5, and lastly processor 7 will be connected to itself. Now, if you split it up, you can think of this diagram like 0, 1, 2, 3, 4, 5, 6, 7. Just assume that virtually you have 2 layers of processors, and this will give you a better visualization of the connection. Processor 0 is connected to processor 0 processor 1 is connected to processor 2, processor 2 is connected to processor 4, processor 3 is connected to processor 6, processor 4 is connected to processor 1, processor 5 is connected to processor 3, and processor 6 is connected to processor 5, and processor 7 is connected to itself. Now the question might arise is that, is this connection arbitrary, or behind this there is some mathematical formulation available? In our computer science, there is nothing arbitrary. Behind every theory, there are some mathematical formulations available, and the mathematical formulation here is this one. Just have a look at the formula, and how it goes like, basically on the left hand side you can see that there are xn minus 1, xn minus 2 up to x0 has been appended one after another, and it is on the right hand side it has been left rotated by a single bit. So how it goes like, say you have a number x2, x1 and x0, you will rotate every bit towards its left, or you will shift every bit towards its left by one position. That means you will shift x0 and replace x1 by x0. Then you will shift x1 to the place of x2. So x1 is here. Now who is on the left of x2? There is nothing. But if you think this in a circular way, x0 is on the left side of x2. So x2 will be brought in place of x0. So if you apply your function to this number, the resultant number sequence will be this. Now what is this xn minus 1 up to x0? This is basically the binary representation of your processor address. This is the binary representation for the processor address. Now if you look into this diagram, you have 8 processors into your multiprocessor architecture, and the address of the processors are 0 to 7. They have been represented in decimal format. Now to apply this formula to find out your target processor, or the processor with which you can communicate, first step you have to follow is you have to convert these addresses to their corresponding binary representations. So the address of the first processor is 0 and its binary representation is 0, 0, 0. The address of the second processor is 1. So its equivalent binary representation is 0, 0, 1. The address of the third processor is 2. So its equivalent binary representation is 0, 1, 0. The address for the fourth processor is 3. So its equivalent binary representation is 0, 1, 1. The address for the fourth processor is 4. So its equivalent binary representation becomes 1, 0, 0. The address for the sixth processor is 5 in decimal format. So its equivalent binary representation is 1, 0, 1. The address for the seventh processor is 6 in decimal format. So its equivalent binary representation is 1, 1, 0. And address of the eighth processor is 7. So its equivalent binary representation is 1, 1, 1. If you follow the formula, then the rightmost bit is x0, the next bit, this bit, is x1, and the leftmost bit is x2. Now what you have to do, you have to apply this formulation to your processor addresses. Let me do this. The address of the first processor is 0, 0, 0. If you shift each and every bit one position towards its left, then you get 0, 0, 0. Hence, by following this formulation, we can say that the first processor whose address is 0, 0, 0 can directly communicate with itself only. So what you do, if you follow the connection line, you can see that the first processor is connected to itself only. Then come to the next processor, which has 1 as its address. If you shift every bit by one position towards left, you will get 1, 0, 1, 0. You can see that the rightmost bit, that is 1, has been shifted one position towards left. Then this second bit, which has 0 here, again shifted one position towards its left. Then the leftmost bit, if you shift one position towards its left, it will come to the rightmost position here. So for the second processor, the destination processor with which it can communicate becomes 2, 0, 1, 0, and its equivalent decimal is 2. You can see into the diagram that the processor whose address is 1 or 001 in binary format has been connected with the processor whose address is 2 or 0, 1, 0 in binary format. Now come to the third processor, which has 2 as its address in decimal format, and equivalent binary representation for the address, that is 2, is 0, 1, 0. If you perform the same left shifting operation for this address, you will get 1 0 0 after left shifting. So the processor whose address is 100, that is 4 in decimal format, is going to be the destination processor, or the processor with which this processor with address 2 can directly communicate with, is the processor whose address is 4. You can see that in the diagram processor 2 has been directly connected with processor 4. Now come to the next processor, that is the processor which has address 3, and the equivalent binary representation is 0 1 1. If you have followed our previous discussion, then you can clearly say that after left shifting you will get 1 1 0 as the destination address, that is equivalent to 6. So in the diagram you can see that processor 3 has been directly connected with processor 6. Then let we move forward towards our next processor, which has 4 as its address. So if you do the left shifting operation for this processor, the address for the destination processor will be 100 after left shifting. That is the processor which has 1 as its address in decimal format. You can see that processor which has address 4 has been directly connected with the processor which has address 1. Now let we move forward. Now come to processor which has address 5. Now if you do a left shifting here, then the rightmost bit which has 1 here will be at the second bit position, and this 0 which is at the second bit will be shifted towards the leftmost position, and the leftmost one, this one, will be brought into the rightmost position. That is, the destination address will be, can you see it in the diagram? Yes, it is going to be processor which has 3 as its address. So for processor 5, it can directly communicate with processor 3. Now come to the 7th processor. 7th processor has 6 as its decimal address, and equivalent binary representation for the address is 110. So if you do the left shifting, you will have 1 0 1 as the destination address, and equivalent decimal representation is 5. So processor 6 has been directly connected with processor which has 5 as its address. Then come to the last processor into our structure. It has 7 as its decimal address, and it has an equivalent binary representation of 111. Now if you do the left shifting here, after left shifting the destination address will be 1 1 1. So this 7th processor can communicate with itself only. So this was the making of shuffle exchange network. If you have followed the discussion, now you know how to connect different processors among themselves by following shuffle exchange interconnection network theory.